Okay, so next topic is about spatial convolution. Ana, cuéntanos algo.
Dice uno rápido, necesitamos sangre. Dice, yo soy cero positivo, pues mala que viene a animar.
Okay, so next lecture is about spatial convolution. So spatial convolution is the same as in one dimension. Let us recall how the spatial convolution is performed in one dimension. So let me go out and let us go. Okay, so let us remind how to compute this. Pablo, cuéntanos, anda.
Dice, hola, ¿cómo te llamas? Hanna, qué bonito nombre, aunque sí.
Okay, so let's say that we have this convolution. So we have y of t that is a convolution of x of t convolved with h of t. So this is a typical response of which kind of filter? This h of t is typical of what? Low pass. What else? Band pass. Band pass, no. The band pass, okay, I'll come to that later. What else can we say about that? Typically causal and first order filters, right? So this response is typically something like this. AT minus T. So this is a first order system. So it is not a band pass because this integral here, this integral is different from 0. And for a band pass, the integral is the value at 0 frequency. So let's do a black again. So h of j0 is equal to this integral, and is equal to that integral. So, and if that is different from 0, it cannot be a low pass filter. So, band pass filters normally they oscillate around 0 because the integral has to be 0. The same for high pass. Okay, so let's remove this. So. Okay, so you may remind that the convolution is equal to the integral from minus infinity to infinity of x of tau h of t minus tau, differential of tau. So that means that we have to draw x, but now in the axis tau. We have to, that is something like that. We have to draw h, but now in the axis of tau again. So, and in the axis of tau, this is h of t minus tau, and this is t. So, this minus tau makes that there is a reversal of the signal, and then the origin that is here. Let's try to make it smaller. So the origin, this one, goes to the point t. So whatever happens here in h of 0 is happening here in the x-axis tau is happening at t, at tau equal t. And then, let's make it bigger again. Then we have to multiply the two. So we have to multiply the two. I don't know how to do that, but let's try. So this is the axis tau, and now we have x of tau, t of minus tau. So it will be something that okay, it has to be done. So it will be something like this, more or less. It is the multiplication point by point of these two functions. And finally, we have to integrate these from minus infinity to infinity differential of tau. So we have to integrate these. I'm stopping here because from t on, there is no value. So all the values are 0. So the integral is also 0. So this area will be y of t. So at every time t, this t is moving with time, and then y of t is this integral. Okay, so that is the convolution in one dimension. Okay. So everyone is clear with this? Yeah. Okay, so then let's see how this is done in 2 dimensions. Okay, so yeah, here we have it. So in general, spatial filtering. So let us do it again in 1 dimension. Before, I think it is nicer to have it in the whiteboard than in the slides. Okay, so this is a filter. Y of t is x of t convolved with h of t. This is a filter, but it is not the only filter we may imagine. So in general, any filter is just a transformation of the input signal, and this transformation will be characterized by some parameters, some function, or whatever. And this one, the convolution, is just a particular case of the general transformation. So, of all possible filters, which is this class? The class of filters that can be expressed with a convolution. What does it mean?
Linear and time invariant.
Linear and time invariant. So those are linear filters. So linear filters are filters that if I have 2 inputs, so if I have 2 inputs that are added to each other, and I convolve with h of t, then the corresponding output is x1 of t convolved with h of t plus x2 of t convolved with h of t. And this is the output of the system to a single one of those inputs. And this is the output to the other input. So this is one of the properties of linear filters. There is a second property, that is that if you have... Don Chitana.
Doctor, ¿cómo está mi marido? Fatal, murió anoche, estaba borracho. Pero si mi marido no bebía, ya, pero yo sí.
So the other one is that if you have an input that is a scaled version of another input, then the convolution of this is equal to this one. That means that let's call this prime, just to avoid confusions, and this is prime. Okay, so if I have two inputs that are added to each other, the output is the addition of the two corresponding outputs. And if I have a scaled version of the input, the output is a scaled version of the output. Okay? Okay, so this is linear. All these that we have been saying. So all this is linearity. That is the L. Okay, what about the time invariant? What does it mean, the time invariant? And again, you are engineers, so you have to write formulas for those. So you can say it with words, but then you have to write the formula. What does it mean that the system is time invariant?
That when you change the input of the system, it's still the same as the first time.
So when you change the input, in which sense?
Like instead of using present values, you use past values, then the output is still the same.
I'm not sure that I get you, but if you have an input, you get an output. Now you shift your input in time, you get the shifted output in time. Okay, so if, intuitively, if I have this input, this is input, and let's say that my output is this one. This is my output. My system transforms this one into this. Then, if I shift, actually this is not a good example. This is not a good example because you cannot see the shift. Okay, so let's make it like this. Then, if you shift your, if you shift your pulse now here, and this is your input, then your output is also shifted, okay, by the same amount. Okay, so let's write that in formulas. So in formulas, that means that if y of t is x of t convolved with n of t, this is the original one without shifting, then x of y prime, that is x of t minus t0 convolved with h of t is equal to y of t minus t0. So this property now is the one time invariant. So convolutions only can represent linear time invariant systems. So these are the only class of systems. This is the only class of systems that can be represented with a convolution. With a convolution with a fixed kernel. Okay, so you can have a convolution, but if the kernel, this is called the kernel. This part here is called the kernel. If the kernel changes with time, so depending if, for instance, let's say, let's make a convolution. Let's go here. So let's say that depending on which t you are, this curve is different. Okay. Then that is a linear, because it is a convolution, it is a linear but time variant system. Time variant. Because depending on which is the t, this curve changes. Okay, so this function also depends on t. Okay? So a convolution with a fixed kernel is only for linear and time invariant systems. Okay, good. So this is what is explained here. So in general, a transformation, a filter is a transformation of an input image to produce an output image. And this transformation will be a function of the pixels at the input, considering a neighborhood, typically in the neighborhood of RC, but you are not restricted to that. Okay? So typically, you take the RC coordinates, look at the RC coordinates are here and there, and then you take a neighborhood. So this neighborhood takes minus S samples to the left, plus S samples to the right. Well, this is column, so this is D to the left, D to the right, and these are rows. So these are minus S to the top, plus S to the bottom. Okay, so you take the RC coordinates, you take a neighborhood around it, and then considering all those input pixels, you apply a function to it to produce an output. And one particular class of transformations are the ones that can be expressed with a convolution. Before going to the convolution, so we have the ones that are based on moving windows. So moving windows is just this idea. Okay? So this idea is you take the central part of your image or of your pixel, the neighborhood around it, and then you produce an output. So let's make it some drawings of this. So we have many possibilities for this. So the most general class is the general transformation. So you have a general T, that is the general transformation. So this is the set of all possibilities. So you can, a new image is just a transformation of an input image. And this transformation can take the values from everywhere in the input image. Okay, so a subset of this is the set of moving windows. So the set of moving windows, J is also a transformation, but now of a moving window I. So that means that, this is not what I want. So let's say that this is my input I, this is my image J, and I want to produce this, the corresponding to this output. So I take a window around it, so actually not in the output, but I take a window in the input around it, make some calculation here, and that calculation goes there. And then I want to produce the next pixel. So for the next pixel, I will take another moving window of the same size, make some calculations, and then these calculations goes there. And now you understand why it is called a moving window. Because depending on what is the value that you want to calculate, in the input, you have a window that is the neighborhood. This is the one that had before from minus D to plus D, and from minus S to plus S. Okay, and the point here was the RC. Okay, so this is C minus D, C plus D, R minus S, R plus S. And then, if you want to compute more pixels in the output, all you have to do is to move your window. And what operation you do within the window, it is up to you. One particular class of one particular class of operations are convolutions. But you know that they represent LTI systems. So here the output is a transformation with some convolution, with some kernel, let's call it A, of the I. And we can represent this as I convolved with H. So this set is contained in this one, and this set is contained in this one. So this is the most general class of transformations. This is a particular class of transformations that looks in windows, and this is a particular class of transformations such that within each window we perform a summation. So we have the general class of transformations. Sorry, this one. This is the general class of transformations. We have the subset of transformations that can be expressed as a moving window. And here you have some examples. So let's say that we have this input image, and then we make a zoom in this region. Then we have it as a matrix of values. Okay, so there is nothing special up to here. And then we take a window. Let's say that I want to compute the output at this location. So what I have to do is to take a window around that location, consider the values within my neighborhood, and then do some calculations with it. And then I want to calculate the output in some other point. Then I take the neighborhood around that point, and I compute and I make my calculations, and the same for another output. Okay, so let's say that my calculation is just computing the average of all those numbers. So at every one of these locations, we already know that we have vectors of dimension 3. So I can take all these vectors and compute the average of all those vectors, and that will be my transformation. So this is called a linear moving window average, or a moving average also. It is a moving average. So you move your window, and within each window you compute an average. Okay, so and here you have the output. Okay, so let's say that I compute a moving average with a kernel of size 9 times 9. So 9 by 9, this is the size of my kernel. So I'm taking 9 by 9 pixels centered on my central pixel, and then I compute the average, and this is what I get. And here you have a more formal definition of the convolution. Okay, so let's do it now. In here, not this one, this one. Okay, so let's try to define. Let's remind how the convolution was written in one dimension. So so let's say yt is x of t convolved with h of t, and this is equal to the integral from -infinity to infinity of x of tau and ht minus tau, differential of tau. So now what about images? So let's say that I have two images, and I have the image at the location RC. These are continuous images because I'm using parentheses. And then I have an input image at the location RC convolved with my kernel at the same location. And now, so now I have functions with 2 dimensions rather than of 1 dimension. So instead of an integral, I will have 2 integrals. Both go from -infinity to infinity. Then I have my input signal, so I have my input signal, but now in a different coordinate system. So I will change my coordinate system to something like this. So rho for the rows, chi for the columns. And I have to integrate with respect to my new coordinate system. And then I have my kernel that is shifted to that particular location. So I will have my kernel that is shifted, but now shifted in shifted to that location. Okay. So now that So now there are two space reversals. So there is one here and another one here. So this time reversal, or space reversal, is reversing in that direction, while this one is reversing in this direction. But now I have the definition of my convolution. And you may remind from 1D signals that that was not the only definition of convolution. There was another one that was this one. And now x of t minus tau h of tau. So it is basically the same, but now it is x that the one that is moving. So before h was moving as a function of time, but now it is x that is moving as a function of time. But both the definitions are equivalent. Okay, so how can I do that for images? So now for images, let's make it black again. So my image at RC would be the double integral. Both go from minus infinity to infinity of I rho, R minus rho, C minus chi, H of rho chi. Initial rho, initial chi. Okay, so both definitions are equivalent. The one in the slide is the second one. Okay, so this is for continuous signals. What about discrete signals? So discrete signals, let's remind how it was in one dimension. So in one dimension, it was like a sum from minus infinity to infinity. And this sum was in m, so x of m, h, n minus n. So it is the same. So these kind of variables, they are called dummy variables. So these dummy variables are the variables that you need to integrate. And here you have your dummy variable, but now in a discrete setup. Okay, so let's extend these to 2 dimensions. So now my image, but now with a square brackets, because we are in a discrete setup, will be a double sum. So it will be a sum in rho, a sum in chi, but now these are discrete variables, so they go like 0, 1, 2, etc. And we have I evaluated at rho chi, and then h that is evaluated at r minus rho, c minus chi. And here the kernel is moving, and you can have the equivalent in which the input signal is moving. Okay, any questions? Okay, so let's go to the slides. So this is exactly what we have. So we have the double integral, and this is the convolution for continuous images. This is the convolution for discrete images. There is some mistake here. So this should be I. So it is I times the kernel. Okay, so the kernel is called the convolution mass, and because of this change of sign, minus rho minus chi, there is a reversal that we will see later in the slides. It is very well represented. Here it is. So there is a time reversal, so or a space reversal. So this is our kernel. So our kernel, you may remind in one dimension that the kernel was reversing. So we have to apply that reversal, but now with respect to the two axes. So we have to revert in rows and we have to revert in columns. So that is the same as computing the mirror of a point with respect to the origin. So actually we will see it. So let's forget for the moment about R and C, but what you see here is that we have something that is minus rho minus chi. So we have to revert in X and we have to revert in Y. So that is computing the opposite. So if you have a point, this is your rho chi axis, and you have this point, then you have to complete the mirror with respect to the origin. So that is what we're doing. That is what we have here. So I have to revert this kernel with respect to the origin. So this point now will go there. And the same happens with all the other points. So they all go to their mirror position. Okay, so then let's go back to series that we are more familiar with. So let's draw now x of m. So let's make it discrete. So we have, this is our signal, whatever, it goes from minus infinity to infinity. And then here we have, let's make it green. So now here in the m axis, we have h of n minus m. That is this thing. And those are signals. Sorry, this is not n. This is n. This is n. Okay, so that means that let's remind how h of n look like. So h of n look like this. And this is now the n axis. So this one here is x of n, right? Because this is n. So this one is x of n. And x of n is multiplied by this sample. But who is that sample? So this sample is h of n minus n. So that is h of 0. Right? What about this one? Okay, so let's take this one here. And I'm running out of colors. So this one here, this is x of n minus 1. And it is multiplied by this one, that is h of 1. And actually, if you think of the summation, let's make it black. This is equal to sum minus infinity to infinity of x of n divided by a of n minus. Okay, so this is equal to, I will start at n. Okay, so this has infinite terms, but I will write the 1 at n. Okay, so when m is equal to n, then it is multiplied by h of 0. When I have x of n minus 1, this is multiplied by m is equal to n minus 1, so this is h of 1. So this is exactly what we have in the drawing. And the same happens on the other side. So on the other side, we have x of n plus 1 is multiplied by h of minus 1. And then you can continue adding terms. And so on. So there is an infinite sum here on the other side. But this infinite sum is what we have here. So in the drawing, we already have that. Okay, so let's keep this one, these two, so that x of n is multiplied by h of 0, x of n minus 1 is multiplied by h of 1. You go to images, you have the same. So the pixel at RC, you don't have it, actually it is not marked, but the pixel at RC is multiplied here by h of 0, 0. That was the same that we had before. And the pixel at 1, R plus 1, C plus 1 is multiplied by h of minus 1, minus 1. And the pixel at R minus 1, C minus 1 is multiplied by H1, 1. So it is exactly the same that we have with one designants, but now in two dimensions. And yeah, this is another representation of the same idea. So this is the input image, this is the output image. We want to compute that pixel. So we go to the equivalent location in the input image, multiply by the kernel. So now the kernel has been written as A, B, C, D, F. So you have to figure out which pixel is multiplied by each one of those values, and you now know that you have to revert to that matrix, and then do the multiplication. Add all those values, and that will be the output in your output image. So let's say that we have this original image, and we multiply by a kernel that is this one, 3 times 3 average. So the 3 times 3 average is this kernel here. So it is a kernel such that, so it is a kernel. I'm only putting the central values. So this is a kind of notation in which you give which are the values that are interesting, and then the rest you assume that are 0. Okay. So it is this kernel. So the central value is this one. This is the one that is multiplying the RC coordinate, and then you have to revert it. But because the kernel is symmetric, it doesn't matter. So it is just the same kernel. So the kernel remains the same. So this is the result. So what you are doing is making an average of each one of the windows. So you take 3 times 3 neighborhoods, give the average there, and that is your output. And you do that, the way I have just explained it can be extended, it can be also understood as vectors, but just the way you have written, they are for scalar images. So you see, this is a scalar. This one here. This is a scalar. So this is one of the channels. So this is the red channel, the green channel, the blue channel, the luminance, the intensity, whatever you want. Okay. You can make it if you put them as vectors. Say this is a vector, then this is a vector, and the comments are still valid. So all the equations are still valid because it is well defined, a vector times a scalar. It would be very badly defined if I made both the vectors, because the multiplication of 2 vectors is not well defined. Let's say it is the inner product, for instance. So the product of 2 vectors, it is not well defined. So let's say that it is the inner product. So the inner product of 2 vectors is a scalar. So this wouldn't be a vector image. Okay, so this one is well defined. The one with 2 vectors is not well defined. But just the way we have explained is for a channel, for a single channel. Okay, good. So this pixel here has been calculated as the average of those. And then next one, and then next one, and then next one. Now you understand why it is called the moving average. Okay. And I think it is a good point to make a break. We will keep only those locations of the kernel, of the mirror kernel, in which the multiplication is different from 0. So this is one of those. And then we have the inverted L. This is an L. So this is an inverted L. And one of the branches of the L is touching the delta. And then we multiply the kernel by the image, but the image is 0 everywhere except for a point. So let's say that this is 1, this is 1, 2. So what we have is 1 times 1, and then we are adding a lot of zeros. We are adding 8 zeros. And then the addition is 1. And then this location here, is this one, we keep it a 1. Okay, good. Okay, then, so as the sum, this is the central location, okay? So we have to keep the 1 at the central location, that is this one. And then we move the kernel to another location that the multiplication is different from 0. So this one here, the multiplication is different from 0. We add all those values and we get another one. So we put it in here, the blue point. And then at this other location, the multiplication is also different from 0. So we get another blue point, and you keep adding, or you keep putting ones in all those places for which the multiplication is different from 0. Now what you get is the same error. That is the one that you should expect. So you know that any kernel convolved with a delta is that kernel, and that is what we are getting. Okay. So, yeah, this is just to highlight the fact that there are kernels in which, if you revert the kernel, you get the same thing. Those are the symmetrical kernels. So, mirroring around this point, so computing, for instance, the mirror of this one with respect to this one is this one. So mirroring is the same as a rotation of 180 degrees. So if you rotate 180 degrees, this is exactly the mirroring. So you can talk of mirroring or you can talk of rotation by 180 degrees. So this kind of symmetrical kernels, you get the same, so you don't have to symmetrize. Okay, so we have seen one way of computing the convolution in which the kernel is moving. But by the formula of the convolution, we know that there is another one, there is another version of the convolution in which the image is moving. Okay, so let's go back to this one. So yeah. So we have seen this one in which the kernel is moving, but we can also express the convolution in this way. So we can also express the convolution as the sum of h of m x n minus m. So now it is the input signal that is moving. And in a similar way as we did before, let us expand a few terms of this one. Okay, so this is h of 0. So when m is equal to 0, x of n plus, it's divided in a different color, plus h of 1 x n minus 1. And now let's choose a different color for this one. So h of minus 1 x of n plus 1. Okay, so this means these terms, sorry, make it black. So this term means you have to take x of n, multiply it by h0. So now we will have, let's say, this was our signal. That is multiplied by h of 0. And I have to add another one. That is, let's make it symmetric so that it is more clear. So let's say this one is there. So we have two samples on the left, two samples on the right. So this is x of n minus 1. So on the same n axis, I have to shift it one sample to the right. So this would be the axis, and now 1, 2, 3. And this is multiplied by h of 1. And then on the same axis, I also have this one. Which is multiplied by h of minus 1. So let's make this is h of minus 1, x of n plus 1. This one here is h of 1, x of n minus 1. And then I have to add all of those. So I have to add all these into a single signal. And the addition of all those, you take this, you add, and then what you get is y of n. So this is another interpretation of the convolution. So the convolution can be interpreted as a moving kernel, or it can be interpreted as a sum of weighted inputs, weighted shifted inputs. Okay. So this second interpretation is called the shift multiply add. And then there is a final way of computing the convolution, that is through the Fourier transform, that we will see in the next lecture. Okay, so yeah, this is just the same that I have been explaining, but now explain a bit differently. Yeah, so this explanation here goes to this formula. So I can also, okay, so let's make it here. Okay, so let's say I have a kernel. I make the drawings in 1D because it is much simpler, right? The same topic applies to. So let's say that this is my kernel. So this is h of 0 delta n, right? So this sample is this one. Then this sample here would be h of 1 delta n minus 1. And this sample here is h of 2, so h of 2 is a scalar, delta n minus 2, and so on. Now when I have to convolve, so let's say I have to convolve, let's make it black. So I have to convolve x of n with h of n. This is equal to x of n convolved with h of 0 delta n, h of 1 delta n minus 1. Do you remember that I told you last day that the Fourier transform is simply a change of basis? Here is my basis. In real space, my basis is made of deltas, of shifted deltas. When I do the Fourier transform, I'm changing this basis of deltas by a base of complex exponentials. Okay, but because of the linearity of the convolution, this is equal to x of n h of 0 convolved with delta n plus h of 1 x of n convolved with delta n minus 1. And this is h of 0 x of n, because x of n convolved with delta is just itself. Then h of 1 x of n minus 1, because if you convolve a delta, a shifted delta with x, then x also shifts to that position. So this is another way of getting to the same idea. Okay. So why you have shifted versions of the input signal that are scaled is because you are decomposing H as a sum of shifted deltas, and then you are convolving with the shifted deltas. Okay, so this is what is explained here. So if you have a delta that is shifted to the location rho chi, and you convolve an image with a delta that is shifted to that location and has some particular weight, what you have is the input image that shifts to that location and is multiplied by that weight. So if I want to compute the convolution, so let's say that I want to convolve this input image with this kernel that has a single delta there at this location minus 16, 16, 16. So then what I have to do is, and the weight is 1, then what I have to do is to take the input image, shift it by this amount, and multiply by 1. And now, let's do it with another kernel. So now this kernel has 2 delta functions, one at the 1616 location with weight 1/2, the other one at the 00 location with weight 1/2. So you keep it as it is, multiply by 1/2, you shift it, multiply by 1/2, and then you add. And then this is what you get. And now we have 3 impulses. So we have 1/3, 1/3, 1/3, and this is what we get. Now we get 3 copies of the same flowers. You see that? 3 copies. Then we may have many more copies. And you may put your delta functions very close to each other, and then what you have is a small blur. If the delta functions are separated, then the blurring is very clear. If they are close to each other, then the blurring is there, but it is not so clear. You're averaging pixels that have very similar value, then you don't notice. But if you make a zoom, for instance, this edge is now a little bit smoother. Yeah, this is the convolution of this kernel. And then let us convert, for instance, an input image with the original image is the image, the red image in I. This is our kernel. So that means that I have to, for instance, the 00. The 00 means I don't have to shift it, and I have to multiply by 800. So you multiply the red image by 800, whatever you get, and you add it there. And then, for instance, this one here. So for this one here, I have to shift my image up, multiply by 8 minus 10, and then copy it to the background. And then the same for all the other locations. And then now you take all these red images and you sum all of them together. So the blue area here is just to represent that when you shift an image, you need more space to do the calculations. And this is also now in 1 dimension. So in 1 dimension, let's say that you have y of n is equal to x of n on both with x of n. And this is a signal that goes from 0 to n minus 1. So it has n samples. And this one here, let's say it goes to n minus 1, so it has n samples. How many samples y of n has? N.
Oh, the one that's the smaller one.
The smaller between n and m, so minimum between n and m. Everybody agrees? I don't agree.
No dijimos que era n más n menos 1.
N más n. So you need a bigger space to keep this convolution. That is what is represented here. Okay, so you need more space. If you want to convolve something that has a given size with something else, and this something else is not a delta, then you need more space to keep that result. Yeah, so here we have the same convolution we did before with the L, but now implemented by shifting our images. Okay, so I have to multiply. So let's keep the L. So let's look at this central pixel. So the central pixel is 0. So I have to take the input image and multiply by 0. Okay. And my input image is delta. Okay. Then, for instance, this one. So this one here, this one here. So I have to shift it to the left, multiply by 1. So I will get this delta in the middle. And the same here, you get the delta, here you get 0, 0, 0, 0, delta, and delta. And now you add all those images, and you get the L again. That is what you expect. So if you convolve a kernel with a delta, you should get the kernel. Yeah, so this is the same. These are different discussions about the same thing. Okay, so now it comes some discussion about how much more space we need to keep our output image. Okay, so let's say that we have an image, an input image that has R rows, C columns. So those are the ones of the black square. This one here. We have these many bands. And we convolve with something that has M pixels, M rows, N columns, and D bands. I can do. We have been talking only of the convolution in 2 dimensions, but now this would be a convolution in 3 dimensions. So each one of the bands could also be convolved with a D. Okay, but just to keep things simple, so let's say that the first layer of this matrix, this is called a tensor. When you have multiple matrices, it is called a tensor. So the first layer of the tensor convolves with the first layer of the input of the image tensor, the second with the second, third with third. You can make it more complicated and make also convolutions in the 3rd dimension, but let's not get into that now. Okay, so how much more space do I need? So I will need a R path, C path, extra rows and columns. And R path and C path are the floor of M over 2 and N over 2. That is, if you think in 1 dimension, it is the same. Okay, so if you convolve with something that is has the origin in the middle, and you have N divided by 2 samples to the left and N divided by 2 samples to the right, then the extra space that you need on the left is N divided by 2, and the extra space that you need on the right is N divided by 2. And the same in the other direction. And then this is what is the pixel or what is the origin after the convolution. So after the convolution, the 0, 0 pixel that was here, now it is no longer in the 0, 0 location of the output matrix. It is a little bit shifted to the center. How much? This much. C path plus 1, R path plus 1. But these are implementation details.
What does floor mean?
Floor, rounding to the floor. So, let's make it. But there are 3 ways of rounding. So, let's take 2 numbers, 0.3, 0.7. And so this will be x. This will be x. Let's organize it like this. 0.7. This is x. So there are 3 ways of rounding. So just standard round. So standard round, you round to the nearest integer. This is 0 and this is 1. That is rounding to the floor. Rounding to the floor is to the nearest integer, but from the floor, from the lower part of this value. And that is rounding to the ceiling. That is this one. Okay. Right. This one is called floor. This one is called ceiling. And this one is called round. Okay, so yeah, and then there are a lot of considerations on how much extra space, and here you have these ideas of R plus M minus 1, C plus N minus 1, so, but these are implementation details that at this point we don't care so much. Okay, so let's say that I have to move this input image with this kernel. So this is a nice representation of the convolution. So we have some delta functions along the diagonal. So I have to shift it by 2 pixels to the left, and then I will have these 3 pixels. Yeah, this is an important thing. Where the origin is in this image. What is the origin of the kernel? So in general, this is something relatively accepted. It depends on the convention of the person writing the code, but in general, if you have a kernel and an image that has let's see, C rows and R columns, the origin, these are R divided by 2, C divided by 2, round, or better than that, for no ambiguity, integer part of R divided by 2, and integer part of C divided by 2. There is no ambiguity because the integer part of 17.5 is 17. So there is no, with the rounding, there is an ambiguity. What do you do with the 17.5? Do you round it up or round it down? So with the integer, there is no ambiguity. The integer part of 17.5 is 17. Okay, so now we have 4 and 4 columns. So where is the origin? So the origin is at 2, 2. So if you start counting, 0, 1, 2. 0, 1, 2, 3, 0, 1, 2, 3, it is here. So for images that have even size, so 4 times 4, for instance, the origin is not at the middle of the image. So let's compare to an image that is 3 times 3. So 3 times 3, the origin is at 1, 1. So this will be 0, 1, 2, 0, 1, 2, and the origin is there. So here the origin is where we expect. For even-sized images, the origin is a little bit shifted. So we could have defined the origin here, but then it wouldn't be in the middle of a pixel. So normally by convention, you define the origin at the middle of the pixel. And it is this pixel here. Integer part of R divided by 2. And okay, so if we look at the kernel that we have, where the can I draw something here? How do you see this? Okay, so the origin is there, okay, because the image is 6 times 6, so the origin is in here. So that is why the input box, when multiplied by yellow, it remains where it is. And then this one has to shift 3 pixels, not 2, as I said. So it has to shift 3 pixels to the left. Sorry. So it has to shift 3 pixels to the left to reach that point. And then it is multiplied by blue. This one is multiplied by purple. It is shifted 2 pixels. This one is shifted 1 pixel. And it is multiplied by red. And so on. And then the final convolution is the addition of all these. And again, there is some convention that is, or not a convention, it is a choice, it is your choice. Which part do you want to keep? So to be complete, you should keep the whole image here, so including these white areas. So, but those white areas, they have not been, they have not been multiplied by anyone. So it is not that they have been multiplied by 0. But it is a bit undefined here, right? So the only region that is fully defined is just the region that has the same size as the input image. And also it is rather convenient that when you compose with something, let's say that you have an image, you do a low pass filter. So the low pass filter, it is convenient that it has the same size as the input one. And then you may decide to crop just the central area. But this is your choice. Strictly speaking, the convolution is wider, but you may crop the central region so that you keep the part that is fully defined. Okay, so yeah, this is the same. Okay, so some examples. So let's say that we have these 2 input images, and we compose with this kernel. So this kernel is just computing an average of the 9 pixels of a small region of 3 times 3 pixels. So you may say that we have lost details because we are computing an average. So an average is always kind of low pass filter. So look at all these borders, we are losing them. And then 5 times 5, 9 times 9, 17 times 17. So, for instance, here we have completely lost this pattern. So this pattern here, look at the 17 times 17. So we have completely lost it. Why is that? Because if you think in Fourier space, okay, so we had an image. Let's make it in 1 dimension because it is simpler. We have an input image, x of h. We are convolving with h. And we have 2 h. We have one that is like this. So it is white, it has 17 pixels. The other one that is very narrow, it has 3. Now let's do the Fourier transform of this. So we know that the convolution in 1D is, so we do Fourier transform. This is the spectrum of this. This is omega. And we have the Fourier transform of the pendulum. So, because of the uncertainty principle, this is compactly supported in real space, so it has to be widely supported in Fourier space. It will be something like that. So this is the transfer function of the kernel. While for the other one, this is much more widely supported in real space, so it has to be compactly supported in real space. And now we are multiplying this signal by either this one or this one. So let's multiply by the red one. So if I multiply by the red, what I get is something like that. So it has very narrow frequency. While if I multiply by the blue one, then I have something that is almost the same that I had. So this is y j omega, and this would be y of j omega. So the frequency content of the red one, that is the one that has been convolved with the white kernel, is much smaller than the frequency content of the blue one. So that is why when you start increasing the kernel size, so now we have a big kernel size, your frequency content is much smaller. So, and the smaller you make it, the more details you keep. You don't keep absolutely all, but you're keeping more. And convolutions can also be very useful to detect borders, for instance. So let's say that I convolve, this is my image. Okay, so I can represent in one dimension my image like this. So it is a pulse, so it is 0, then 1, then 0. And then I compute the difference. I compute the convolution with this kernel. So this kernel, it is not shown the kernel, but yeah. We are showing just the result. But let's say that my kernel is this one. So H of RC is equal to delta RC minus delta RC minus 1. So this means keep the image as it is, shift the image by one column to the right, invert it and subtract it from the original. Okay, so that is what we are doing here. So I'm keeping the image as it was, and then shifting it one pixel to the right, inverting, and then summing. So for instance, here I'm subtracting this image. So let's keep this in mind, and now you shift it by 1. So we are subtracting at this point, for instance, 0 minus 0. So it is 0. And it is 0 all the time up to this point. So we are subtracting 1 minus 0. So that is 1. And then at these locations, we are subtracting 1 minus 1. That is 0 again. At this point, we are doing 0 minus 1. That is minus 1. And then it is 0 again. So now, by convolving with that kernel, I am detecting edges that go from low to high when they go from left to right. So from left to right, when you go low to high, you get a 1. When you go from high to low, you get a minus 1. And if instead of that kernel, you use this kernel, that is almost the same one as this one, but now the shift is performed to the left rather than to the right, then it is the opposite. When you go from low to high, when you are traveling left to right, now you get a minus 1. And if you go from high to low, you get a 1. And if you add the two kernels, So now we can add the two kernels. So if I add the two kernels, then I get an edge detector that detects edges when you go from low to high or high to low, and they are more or less symmetrically detected. And yeah, and you can do the same in the other direction. So with this kernel here, you detect this kind of borders. So you detect vertical borders. With this kernel, you detect, sorry, these are horizontal borders. Now vertical, these are horizontal borders. And then if you add the two kernels together, so this kernel plus this kernel, then what you get is an edge detector in all directions, for vertical and horizontal directions. And I have been explaining with -1 and 1, but the same applies to 0 to 55, so it doesn't matter. Okay, so now let's convolve this image with, for instance, the vertical difference. The vertical difference is this one. Vertical difference is this one. So let's convolve with that. So all the borders along this direction, we should see. And we are seeing, for instance, here it is very clear. So this pattern here completely disappears with that convolution. You see, completely disappears. Only these small details here, because there was a change in the gray values. And the same would happen with some of these borders, not some, all of them. So the separation between the squares here, we don't see it, because they are not, when you differentiate in this direction, they don't appear. There is no difference in that direction. And the same happens with the house. So the house, for instance, this wall of the house completely disappears, because in this direction there is no difference. There is a difference when you go in this direction. So if you convolve with the vertical difference kernel, this...
Juan, lo tengo yo. Perdón.
Now this is the same with the horizontal differences. So now these are the patterns that disappear, and the borders in this direction will disappear again. And horizontal plus vertical differences. You can have diagonal differences, and so you can put the -1, 1 instead of vertical or horizontal. You can put it in the diagonal as well. So now you can compute derivatives in directions, in diagonal directions. This the other diagonal. These are the two diagonals. Actually, we have the kernel here. We have the kernel. This is this kernel. Now you can add the two kernels. Now you have the two diagonals. And you can add the horizontal, vertical, plus diagonal differences. So now we have an edge detector in all directions. And here are the same original images. Any question? So convolution. Now we have seen two uses of convolution. One to compute averages and local averages. And we see that they blur the input images. And the other one is to compute edges. And all image acquisition devices, they somehow have a low pass filter response. So in a very rough approximation, they can be simulated by convolving with a kernel that is somehow computing an average. You can put different weights, so the differences between different devices is what are the weights. But they are all kind of computing low pass filter images. Okay, good.